So here's an example, okay? So we have methane gas, propane gas, octane liquid. Okay. So the nature of these London dispersion forces is that they actually really like to explain the boiling points of certain substances. Okay? So when we say boiling point, that means that you can either be a liquid or a gas, depending on the temperature that you're at. Okay? So methane is a small molecule. Okay? So if we were to kind of think of like methane, okay, this is what it looks like. Now, think about the number of electrons that are involved with the carbons and the hydrogens in there, okay? Out of these three molecules, this one actually has the lowest amount of electrons around it, okay? Now, all of them have nuclei that those electrons are going to be attracted to, but because there's so few electrons, those attractive forces between, let's say, a methane and another methane, they're not going to be as big because there's not as many electrons to kind of be distracted by the other methanes that are around it, okay? So this explains why this methane gas is a gas, okay? It has a very high or low boiling point. So at room temperature, it's already going to be a gas because that's just what we happen to see because it has very low London dispersion forces, okay? It has London dispersion forces, but it's not a very significant amount, okay? Now propane, we know that propane is also a gas, okay? But it actually happens to be a bit of a heavier gas. So when you have this propane, this is what the structural model would look like, okay? This one would have more London dispersion forces because there's a lot more electrons that are going around these nuclei. So a propane gas molecule is going to be attracted more so than the methane ones were because there's more electrons to kind of distract it, okay? So there's even more electrons here, but this is still a gas. Okay, so there's lower electrons, but still more than the other one. But at this point, this is still a gas, okay? But in reality, this one would actually have a higher boiling point than the methane gas would, okay? But it would still be a gas at room temperature, okay? Now this last one, this is octane, gasoline, okay? What do we know about gasoline? Is it gas? No, it's a liquid, okay? Now look how many carbons and hydrogens are involved, okay? That just means there's a lot of electrons. And I'm just going to quickly draw this out. 1, 2, 3, 4, 5, 6, 7, 8. Whoop. And I just not write out those hydrogens. Okay, but this is what the structure of octane looks like. Okay, so there's lots and lots of electrons that are going to be fluttering around this molecule. And as a result, it's going to find another octane. They're going to be like, okay, well, that nucleus is closer than my original nucleus. So they're actually going to be sucked in more, okay? Now, in terms of like the particle model of matter, what do you look like when you're a gas? Particles are super far apart, right? When you're a liquid, what happens to your particles? They're closer together, okay? So this would be a gas. At this point here, if it's like this, let's say, okay, and there are smaller spaces, they're still moving, okay? This would make it look more like a liquid. So the higher that attractive force, the more sucked in those little electrons are going to be to each other, the more sucked in those molecules are going to be because of those London dispersion force attractions are going to be, and then therefore you're more likely to look like a liquid, okay? So in this case here, the rule of thumb, the larger the molecule, the more likely the molecule will have a higher boiling point and therefore be less like a gas but more like a liquid, okay? And just depending on how those particle models, and this is why we have to know the particle model of matter, it all comes down to this. Why is it that water happens to be a liquid, okay, even though it's a small molecule, okay, it has this special nature of having more closer little molecules between each other than further apart, and that's why it's not a gas at room temperature. Okay, so the other thing too, all molecules have London dispersion forces. Okay, so in the example that I gave you guys, I could very well ask you guys to tell me which of these three molecules has is more likely to be a liquid, or which one of these has the highest London dispersion forces, or which one of these has the lowest London dispersion forces. Okay?